Hi everyone. This lecture is provided for Tuesday, November 7th, 2017. This is class number 23. Just as a starting announcement, this lecture is going to be online as well as Thursday, November 9th. The class meeting for that day is going to be online. I'm out of town this week, so hopefully you find these videos without any trouble. As some other announcements, homework 6A will be due on Thursday the 9th by 11 a.m. You should submit that assignment electronically according to our normal procedure. The homework 6B is due on Tuesday, November 14th. And also on Tuesday, November 14th, we're going to be back meeting in person live in our normal time, our normal place, and that's when we're going to have exam 2. As I've described in a previous class meeting, the equation sheet is already provided online if you want to have an early look at which formulas are provided and where they are on the page, although there's no need for you to print that because I'll bring paper copies on the day of the test. Today's lecture is going to be related to momentum applications in Chapter 6, some of a continuation of the things that were introduced in the last class meeting. Specifically, we're going to be talking about fluid jets and vanes. So if you have any questions regarding the material, I'd encourage you to feel free to send me an email. Although I'm out this week, I'm going to be doing my best to respond electronically where I can. And that goes for the announcements as well. If you have any questions about the scheduling or concerns, please feel free to let me know.
All right. So there's three main types of problems in Chapter 6. There's the type of problem where we've got a fluid jet coming in and either striking an object or causing some sort of a force as it is intercepted. And so here's an illustration of a fluid jet. The jet that's moving through the air doesn't have any pressure, but it does have a mass flow rate and it's got a velocity. And so the change in velocity is what causes a force that has to be applied. And so what would happen to this system that's shown? It looks like a tank on rollers. If we cut this tether, what would happen? It would slide which direction? To the right. And so the external force we have to apply to that system to hold the system steady is, just by inspection we can see that it's to the left. All right, so that's one type of problem, is fluid jet problems. Why is it relevant that they've told the 60-degree angle in this case? Who cares what the angle is? Well, why does it matter? We care. So force in the x direction, right. So remember, when we apply the momentum equation, we can do it in directions. There's the force required in the x direction to hold the system steady, and there's also going to be some force required in the y direction to hold the system steady. So in a case like this, they're telling us the angle so we can find the component of the velocity that's in both of those directions. All right. There's also vane problems, and a vane simply changes the direction of flow. It can be an open jet like this, or you can have vane problems where it is like an enclosed pipe that's changing the direction of flow. In either case, what's causing a force having to be applied is simply that the direction is changing. The velocity is different. And so if you look at this, you can sort of think about what happens when you put your hand out the window. Your hand is intercepting a flowing fluid as you drive through the air. When you put your hand out, you have to apply a force to your hand through your arm to hold your hand steady. And so think about it. What direction, what external force do you have to apply to hold this system steady? It's going to be to the left. And what about vertically? Do you have to push up or do you have to push down to hold this system steady, meaning the vane itself? You have to push the vane down because the liquid is going to be pushing up on the vane. And we're going to be very careful today to distinguish between whether it's the force holding the system steady or the force that the liquid is applying to the system, because those are equal and opposite reactions. And if you make a mistake on the exam and identify one instead of the other, then that's more than just sort of like a negligible mistake. I mean, it's not the end of the world, but it's something that you have to get right. Finally, there are nozzles. We're going to talk about nozzles on Thursday, so we won't have any examples related to nozzles, and the first homework that you're turning in doesn't yet have nozzle problems, but it's the third of the three main types that we'll be addressing. And what makes it unique is that we have to account for pressure in the case of a nozzle. Because a nozzle like this, what this is there may be a jet of liquid coming out of the nozzle, but on the upstream end of the nozzle, it's a pressurized pipe. And that throws kind of a complication into the way that we account for the forces required to hold the system steady. So in all of these cases, the main equation that we can apply is this one. And it may be that we also look at things in the y direction. If, like for the vane problem, we have a y component of velocity, and in the fluid jet illustration shown at the top, there would be a y component. And always remember the interpretation of the left-hand side of that equation. It's the force required to hold the system steady. All right. Okay, so let's look at this one. We have a jet that's coming in at a 70-degree angle, and there's a certain amount of liquid already in there. Currently, there's 20 liters of water, and the tank itself has a mass of 5 kilograms. And so we want to find forces in two directions. First of all, in the x direction, this is asking what is the force that the stop block applies to the tank? And then in the y direction, what is the force acting on the bottom of the tank? Okay, so before we start thinking about numbers, let's just think qualitatively. How does this relate to the equation that we've just seen, where the left-hand side is interpreted to mean the force required to hold the system steady? Is this asking for you to solve for the force required to hold the system steady, or is it asking what force does the moving fluid apply to the system? So what do you think? What about this first one where it's talking about the stop block? I guess the stop block is here to make sure that the tank doesn't slide to the left. So is the force that the stop block applies to the tank, is that the force holding the system steady, or is that the force that the incoming jet applies to the system? Holding the system steady. So we're pushing, that stop block is going to be pushing to the right with some force, and if it wasn't there, then the system may not be steady. It may start to slide depending on the friction of the bottom of the surface there. And then the same thing is true about the force acting on the bottom of the tank. The table or floor or whatever that surface is going to be pushing upward to support the weight of the water, the mass of the tank, and also in reaction to the incoming jet. Okay, so for this one, what we're going to do is apply the momentum equation in both of those directions. So the two directions that we're going to do it are going to be the x direction and the y direction. Now there's some preliminaries that we can calculate. The tank, we know, has a mass of 5 kilograms. We can find the area of the jet based on the diameter that's provided. You can find the weight of the tank. You can find the weight of the water. And then we'll consider the momentum in the x direction. And to do that, the equation we're going to apply is the sum of the forces in the x direction are the mass flow rate out, velocity out in x, minus the sum of the mass flows in times the velocity in x. All right, so the out, there isn't any. There's only a stream coming in. And so that's going to enable us to cancel out this out term from the momentum expression. We'll need to calculate the mass flow rate in. That'll be in kilograms per second, of course. Now, what about the velocity in an x? What are we always careful to do about velocities in momentum problems? The sign. Right. So remember we talked about how our standard notation is to the right means a positive velocity and to the left is a negative velocity. And so the velocity that you put into this is going to be not only careful attention to the sign, but also the component that's in the x direction. And so since there's a 70-degree angle, most of that velocity is vertical. Only a smaller fraction of it is going to be in the x direction. So you'll need to account for the 70-degree angle. And then we can look at things also in the y direction. Okay, so in the y direction, we'll say the sum of the forces required to hold the system steady are the mass flow rate out, velocity out in y, minus the sum of the mass flow rate in, velocity in y. As before, there's no outflow, so this term cancels out, the first term, but there is an inflow. Inflow, mass flow, even though it's going to be down, we don't put a negative sign in the mass flow. Mass flow rate is a scalar, which only has magnitude, but velocity has sign. And in this case, since it's downward, we have to be careful to put the negative velocity in there, and then we need to find out what fraction of that velocity, 15 meters per second, is vertical instead of horizontal. All right, so I'm going to stop talking and give you some time to get through the calculations on this. I'll be circulating around to verify what you've done. All right. It's not a bad idea on problems like this to put a sketch on the paper, even if you're looking at one in the book. Just somehow the process of drawing a sketch will help you to visualize the forces involved, I think. So we calculate the weight of the tank and the weight of the water. That's going to be two of the three components that accounts for the vertical force that the table has to push up to resist. But now in the x direction, only a small fraction of the velocity, 34.2% of the velocity, is in the x direction because of that 70-degree angle. We take the cosine of 70 to get that factor. And the reason why the force is to the right is because, remember, we have the negative sign since it's the inflow. You know, the second part of this term is the inflow term, so that negative sign is there. But then, since the velocity is to the left, we have the negative sign there, and so it becomes positive. And so the force is to the right, and that kind of just matches up with our intuition that you'd have to push on that to the right to prevent the container from sliding to the left due to the jet. We've all been sprayed by hoses before, right? We know basically what the jet is doing. All right. So that's the x direction, and then the y direction. Same kind of thing where we're canceling out the outflow term since there isn't one. Finding the force is up. We have to push up to resist that jet impacting the tank. But then there are also the weights of the tank and the weight of the water. And so the overall force. You'll notice that in both of these cases, I put some sort of a note to indicate, to reinforce the direction. Even though positive numbers means up and to the right, I still try and emphasize that just to drive the point home, that this is to the right. The interpretation of this is that the force will be upward, and I encourage you to do the same thing to remove any ambiguity about whether you know or don't know the directions of the force. Any questions about the example?
I guess I'm just confused by the wording. It says the force acting on the bottom of the tank.
Yeah.
So wouldn't that force be downward onto the bottom of the tank?
All right, that's a great question. I think you have a career in law that you could pursue. All right, because you could say the bottom of the tank has two sides, right? There's the inside bottom of the tank, and then there's the outside bottom of the tank. And so what I was thinking when I wrote that is you have the bottom of the tank, the exterior outside bottom of the tank. There's a force that's pushing up on the tank in the sum of its weight, the weight of the water, and the force. But if you're looking at the bottom of the tank from meaning the inside of it, then that would be a different story. So it would be the same magnitude but opposite direction. Yeah. All right.
How do you calculate the weight of the water?
The weight of the water is calculated from the volume and the density.
You convert it to cubic meters and then times it by
You can't. 1 liter is 1 kilogram. Yeah, that's just either that or divide by 1,000 and multiplied by 1,000. All right. Other questions? All right. For those of you who have already looked at the homework, I think you'll realize that this is pretty close to one of your problems. All right. So here is a vane, and it's deflecting the direction of flow. Now in problems like this, sometimes they tell you that the velocity is the same after the magnitude of the velocity is the same after the impact, meaning that it didn't slow down from coming into contact with whatever this deflector plate is. But in this case, the velocities are different, which means that there must have been some sort of an energy loss or a drag or something, because the incoming velocity is 11.5 meters per second. And then if you look at the magnitude of the outgoing, here it's 10.8, there it's 9.9. And so the velocities aren't the same. Now, this problem is saying, what forces in the x and y direction does the water jet apply to the deflection plate? So how does that interact with the formula that we've seen before? Remember the force required to hold the system steady. Yes? Mm-hmm. Not necessarily. I think the reason why the velocities are different is just because there's contact with the surface. Maybe it's the length of contact with the surface is causing like a frictional loss. And so it's probably meant to just sort of simulate that. A contact loss that's reducing the velocity. Now that's not to say that the flow rate in still equals out. You know, just because the velocities are changing, that doesn't mean that there's accumulation around the vane. It's still the case that jets 2 and 3, the overall mass flow of those two is equal to the mass flow at 1. So in equals out here. There's no place that the water could be storing and accumulated. It's just all open to the atmosphere. There's no tank. Okay, but back to the question of what about directions here? So since it's asking what forces does the jet apply to the deflection plate, that's the equal and opposite reaction that you'll calculate using this formula. So you'll still use this formula, but then at the end you'll think, this told me the force required to hold the system steady, but what the question is asking is what force does the water apply to the vane? And normally, when we're using this equation, it's the opposite. It's what external force do we have to apply because of the water. So it would be the opposite sign. Okay. So obviously in this problem, you're given the mass flow at 1, but you need to calculate the mass flow rate at 2 and 3. And the way you can do that, the key, the one piece of information you've got is here at 3, it's a circular outflow jet with a diameter of 2 centimeters. And so that's going to allow you to find out how much of the mass flow is in stream 3 and how much of the mass flow is in stream 2. Because 1 is equal to 2 plus 3. All right. So the steps are similar to what we did before. There isn't going to be a weight of water that you have to worry about, but you're going to need to calculate the mass flow rate at 2 and 3, and then start considering what component of the force is in the x direction because of the angle that's given, and what component is in the y direction. Okay, so we've got a beautiful sketch to get things started, and now just by looking at it, we can kind of tell that we're going to have to push the water, it will push on that plate to the left. I mean, that should sort of be instinctively obvious, and then up if more of the mass is going up than down. So it's maybe not quite so obvious before we do the calculations, but I guess maybe from the angle of the deflector plate that gives us a hint. Anyways, the first thing to do is calculate what are the mass flow rates, and in equals out. So mass flow rate at 1 is 6.7 kilograms per second, and then we can use the diameter that's given for 3 in order to calculate the mass flow rate there is 3.11 kilograms per second, and then the mass flow rate 2 is just everything else that's left that isn't in stream 3. So that's 3.59 kilograms per second. All right, so for the x direction, the most common oversight that I noticed when I was walking around is that, remember, since the jet in the x direction, since this outflow is to the left, then we need to put a negative sign there for the 9.9 meters per second when we're substituting in. So this is a case where there's actually 2 different out streams. And so in the formula, when it says the sum of the mass flow out, velocity out, then that means there may be more than one stream, and that's the case here. We've got 2. And so the 3.59 times 10.8, that is the stream that's exiting at 2, and it's to the right, times cosine of 70 gives us the x component. And then the negative 9.9 is important for the velocity of that other stream. So when you do it all together, 74.32 newtons is the force of the jet on the plate. And we do the opposite because when you solve for the sum of the forces in the x direction, it's negative 74. So this was asking for the force of the water on the plate. So it's the opposite. And then in the y direction, negative 7.5. All right, so we've got 3 minutes for me to show you some key ideas for a couple of the homework problems that's due on Thursday. Now 2 minutes. All right. This is asking you if there's a jet of water that impacts the plate and you have to push 200 pounds to the right to hold the system steady, then what is the velocity? So we've been calculating forces today, but you can switch things around and put in a known force. So it'll be negative 200 pounds to the left is the force that's being applied. The mass flow rate you can calculate because the volumetric flow rate is given, and you multiply it by the water density of 1.94 slugs per cubic feet. And remember, that's what you have to do in order to get pounds, is you're multiplying the velocity times to get the mass flow rate in terms of slugs per second, and then the velocity will give you the force. And so if you are drawing the control surface, the place to draw it here, where you're keeping track of where the change is where the flow is changing direction. And so here's your in the x direction. There's no out in the x direction, just only in. So you'll cancel out that first term of the equation because there's no out in the x direction. And finally, for this problem, it's interesting to note that the velocity is the same. It's basically like there's a plate with a hole in it. This jet the hole allows some of the water to go out, some of it's just deflecting in the y direction. And so for this one, you need to find the difference mass flows in and out, because the diameters are different. That means that the mass flow rate in is going to be much larger than the mass flow rate out, but the velocities are the same. You can ignore what's happening in the y direction. They're just asking what external force in the x direction, essentially. We assume that in the y direction everything is sort of fanning out equally in y, but it's just in the x direction. All right, that's it for today. I'll see you in class on Thursday. I hope everyone remembers to vote. It's election day.